Hello everyone, my name is Joshua Anakan Acosta, and in this video we are going to discuss three types of antennas. So, the three types of antennas that we are going to discuss is based on my first name, my middle name, and my last name. So for the first letter of my first name, we have the slot antenna. For the first letter of my middle name, we have waveguide. And for the first letter of my last name, we have loop antenna. So first is the slot antenna. So it is composed of a metal surface, so usually a flat plate, and it is also uh, composed of one or more holes called slots. And it operates at 300 megahertz to 30 gigahertz. So this is an example of a slot antenna which is a rectangular in shape. But we can also have any kinds of shape, such as the annular slot antenna. So the slot inside the metal surface is circular in shape. Or we can have a more complicated shape, such as the annular ring slot antenna. So it is kind of like a circular but a more complicated kind of shape. So how does the slot antenna work? So it is based on the Babinet's principle, wherein according to this principle, the structure of the slot antenna and the half-wave dipole structure cut out from the conducting sheet are complementary to each other. So it means that the conducting sheet and also the slot which is cut out from the sheet are complementary. So what do we mean by complementary? It means that they are almost share the similar antenna properties. So here is an example of a uh, slot antenna. So the conducting sheet here is rectangular in shape, and the slot inside the conducting sheet is formed as a complementary half-wave dipole structure. So how do they differ? So they only differ in the polarization. So here is our diagram. So for the slot antenna here, we have a horizontal polarization because the waves here are propagating horizontally, whereas for the complementary dipole antenna, so here is our antenna, here is our dipole with a length of half of the wavelength. So the charges inside the uh, conductor here in conductor A and B here is fluctuating, resulting in a electric field or electromagnetic propagation, which is vertical in orientation. So they only differ in polarization, but they almost have the same properties. So next, we are going to calculate the slot antenna impedance. So in this video, we are just going to calculate the rectangular slot antenna impedance. So the formula for our slot antenna impedance is Zs times Zd is equal to 1/4 times n sub 0 quantity squared. So the Zs here stands for the terminal slot impedance, the Zd is the terminal complementary dipole impedance, and the n sub 0 is the intrinsic impedance of free space. So we know that the intrinsic impedance of free space is equal to 376.7 ohms, and we also know that the characteristic impedance of the terminal impedance of our half-wave dipole antenna is 73 plus J42.5 ohms, because this is a half-wave dipole antenna. And substituting the values, we will get the impedance of our slot antenna, which is 363 minus J211 ohms. So next is the waveguide. So the waveguide is a structure that guides electromagnetic waves. It minimizes loss of energy by restricting transmission to one direction. So here is an example of a simple rectangular waveguide. We can also have flexible waveguides. So this is also a rectangular in shape. Or we can have different shapes such as this waveguide here, the T waveguide. And lastly, we can also have a circular shape with a wave for the waveguide, and as simple as this one. So it just uses a can here for the waveguide and a vertical antenna here to send and to transmit and receive signals. So waveguides can be rectangular or circular in shape. So it is made of brass, copper, or aluminum. And it is primarily used at microwave and optical frequency ranges. So these are high frequencies. So here is our waveguide dimensions. So for our rectangular waveguide, we have the waveguide name. So we have three standards organizations here. So they have different naming systems. So here is the recommended frequency range of the electromagnetic signal or wave that is being propagated inside the waveguide. However, this is only the recommended frequency. It can exceed above this or below this range. And the maximum, or I mean the cutoff frequency of the lowest order mode here, the lowest value of the frequency that we can have for the EM waves inside the waveguide. So this one is the cutoff frequency of the lowest order. And the cutoff frequency of the higher order or the next mode is this one. So the properties of the waveguide is dependent on its inner dimensions. So we have the A. So here is our A, the length, and our B, which is the width. So this is measured in the inner side of the waveguide. So we also have the double ridge waveguide. So its properties for the cutoff frequencies also depend on the dimensions of our waveguide. And lastly, we also have circular waveguides. So it also depends, I mean the frequency inside the of the EM waves propagated inside this circular waveguide is also dependent on the diameter or the radius of our waveguide. So we can also have different flange types. So the flange here is this cylinder here, which is used to connect it to other waveguides. So we can have a square type of flange. We can also have a round type. So this circular waveguide here has a round type, I mean a round flange type. And we also have waveguides that convert from other shapes to another shape. So here we have a circular waveguide which is converted to a rectangular, and also from a rectangular converted to a circular. So we should take note that waveguide is not exactly an antenna. And that is because antennas, the definition of antennas is that they transmit or receive electromagnetic signals, whereas the waveguide just guides or just guides the propagation of these EM signals. However, waveguides can be used with different antennas. So for example, we can combine the waveguide with a slotted antenna, which is called a slotted waveguide antenna. So the waveguide here is, uh, there are slots inside the waveguide, and it also, uh, the electromagnetic signal that is propagated also depends on the dimensions of the slots. Or we can also have the horn antenna, which is composed of a metallic horn here and a waveguide here. And take note that inside the waveguide, we have a small rod here, which is the antenna part of the waveguide, wherein this rod here transmits or receives electromagnetic signals. And lastly is the loop antenna. So a radio frequency current carrying coil is given a single turn into a loop and can be used as an antenna called as loop antenna. The currents through this loop antenna will be in phase. The magnetic field will be perpendicular to the whole loop carrying the current. So the loop antenna, the frequency range of the loop antenna is between 300 megahertz to 3 gigahertz, which is also called as the ultra high frequency or UHF range. So here are the classifications of loop antenna. So according to shape, we can have circular, rectangular, triangular, square, hexagonal, and many more, as long as it forms a loop. And we can also classify the loop antenna according to its size. So we have a large loop and a small loop. So what do we mean by the large loop and small loop here? So it depends on the wavelength of the electromagnetic signals that is being transmitted or received by the loop antenna. So we will discuss it later. And also we can classify loop antenna in the number of turns. So we can have a single turn. So this is a single turn circular antenna. Or we can have multiple turns. So this is a multiple turn rectangular loop antenna. So next, we have the large loop antenna. So it is also called as resonant antennas. And the reason why it is called as resonant antennas is because, okay, let us discuss the reason why it is resonant antennas later. So it also has a high radiation efficiency, and this is the reason why it is called a resonant antenna. So that is because the length of the loop is equal to the wavelength of the electromagnetic signal that is being sent, transmitted, or received. Next is the small loop antenna. So it is also called as magnetic antennas. So it is less resonant compared to the large loop. It is mostly used as receivers, and usually the length of the loop is equal to 1/10 of our wavelength of the EM signal. So here is the radiation pattern of our loop antenna. So here is a two-dimensional view of our radiation pattern. So as you can see here, this is the loop. So this is actually the top part of the loop. So the loop actually is actually here at the center, and the propagation of the electromagnetic signals is horizontally here. So for the 3D, so for the 3D version, we can have this one. So the loop is horizontally in the uh, parallel to the X and XY plane. Okay, and the propagation of the wave is also parallel to our XY plane. So it is also horizontal for the propagation. And here, okay, so as you can see, we can compare the loop antenna and the half-wave dipole antenna. So actually, they have the same polarization or direction of the electromagnetic signal propagation. So for a horizontal loop, we have a horizontal propagation, and for an antenna here, we can also have a horizontally polarized antenna here. So actually the half-wave dipole antenna is vertically oriented in its physical form, and its polarization is horizontal, which is the same as our loop antenna. So next, we will compute for the small loop impedance. So we will skip the computation of the large loop because they are resonant antennas. So first, for the small loop impedance, we have a radiation resistance, which is the real part, and this is applicable to any shape of the loop. So the approximated formula here is 177 times n times s divided by lambda squared quantity squared. So the n here stands for the number of loops, the s stands for the surface area of the loop, okay, and the lambda stands for the wavelength. So next we have the loop inductance, which is the imaginary part. So we will compute for the loop inductance of A. This formula is just for the circular shaped small loop antenna. So the formula is 2 pi times f times mu times a multiplied to ln of 8a over p minus 1.75. So wherein f is the frequency, mu is the permittivity of the conductor, which is equal to the permittivity of free space multiplied to the relative permittivity of the conductor. So the conductor here is, it refers to the loop, the material used for the loop. So the A here is the radius of the loop, and the P is the radius of the wire or conductor that is the material of the loop. So here are the common loop antennas that is being used. So the commonly used loop antennas is the circular loop antenna and the square loop antenna. And they are mostly used as AM receivers because of high signal to noise ratio. So they are used in AM radios. So amplitude modulation. And this is the end of our presentation, and thank you for watching.